Friday, we're going to use those same 12 graphs and go through each one and talk about the types of discontinuity. So that's like a break in the graph if it exists. And then after we do those 12 graphs, then you're going to have your exercise number 5 to 8. Okay, so let's talk about graph continuity. So when we're talking about graphs or functions, we can say that a function is continuous, okay, at a point. So x equals a, that's like a random x value that I'll always give to you. So we can say a graph is continuous at that point if the following conditions are met. So there are 3 things that need to be true in order to call a graph continuous. So the first one is the function exists at that point. So what I mean by that is, say I asked you for like f at 2. You don't have to write this down, but say I asked you for f at 2. And say you went to the graph and you were following along and you got to where x equals 2 on your x-axis. And at that point, you have a hole in the graph. That would mean that it doesn't exist. The function doesn't exist at that point. So we would need to make sure that we actually have a true value at that point. So the graph exists at that specific point. Okay. The next condition that has to be met is the limit has to exist. So this is what we did on Friday. On Friday, we checked that the limit as x approaches a random number from the left is equal to the limit as x approaches that point from the right. Remember, we always checked, does the left-hand side equal the right-hand side? And if it does, then we can say the limit exists. If those two are not equal, that's where we had the case of the limit not existing. Okay, so that's the second condition. The limit has to exist. So the left-hand side and the right-hand side have to be equal. And the third and final condition is, so I can't erase that. The third and final condition is that these two are equal. Okay, so that's what I've written for you. Whoops, so that's what I've written for you right here. That this point, that random a value I give you, okay, first of all, it has to exist. We have to be able to find a y value at that point, and it has to be the same answer as the limit. Okay, so don't worry, we're going to go through a whole bunch of examples, but essentially we want the function value at that random point to be equal to the left-handed side limit, and then that's also equal to the right-hand side limit. So we need all 3 of these things to be true and equal to each other. And if that's the case, we say the graph is continuous. If any of these 3 things are not true, then we say the graph is discontinuous. Okay, and we're going to go through the situations for that right here. Okay, so a function is discontinuous at that point if the function is not continuous. Obviously, if it's not continuous, then we say it's discontinuous. Okay, so again, if any of these 3 things are not true, we can safely say it's discontinuous. And there are 3 specific types of discontinuity, and you're going to have to memorize these 3 types of discontinuity and the difference between them. And I have pictures here as well for the visual. Okay, so we'll say something is discontinuous with a removable discontinuity if the function value does not equal the limit. So what that means is this value we get when we check the function at a random x value, that answer that we get does not equal the limit. Okay, so I just want to specify though, this here means that the limit does exist. Okay, so it's like I checked the left side, I checked the right-hand side, so the limit does exist, so that's all good, but that answer for your limit does not equal the function value at a point. So I'm just going to show you what I mean here. This is what I'm looking at right here. Here's removable, okay? So if I check the value of this limit at this point right here, so I'm going to use my value as x being equal to 2. That's what I'm looking at, okay? If I check the limit from the left-hand side, if I approach 2 from my left-hand side, I am approaching a value of y equals 1, right? That's what we did on Friday. And then if I also check it from the right-hand side and I approach that x equals 2 value from the right-hand side, same thing, I get a y value at 1, right? So we can safely say that the limit as x approaches that 2 value does exist. So of our random function, it does exist and it is equal to 1. And I have checked that the left and the right are the same. So our limit exists at 1. But now if I check the actual function value at that x value, x equals 2, if I go to x equals 2 and I actually check that true value at x equals 2, it does not equal 1 because it's an open circle, right? This point right here is like 2 and nothing. It's undefined, okay? It can't exist there. So the function value at 2 does not exist, okay? So that's why it's removable. So removable is always going to look like kind of a nice, straight, solid line, but typically there's a hole in the graph. All right, that's removable. Okie doke. The second is called a jump continuity, or sorry, discontinuity. Jump discontinuity is when the left-handed limit does not equal the right-handed limit. So we're not even worrying about that f of a thing here that we were worried about in the previous one. We don't need to check f of a. As soon as we see that our left side answer is not the same as our right side answer, then we know the limit does not exist, and that would be classified as a jump discontinuity. So let's look down here. This is what a jump discontinuity looks like, and you can literally tell, whoops, we can literally tell because it literally looks like, sorry, my pen's not working. It literally looks like the graph jumped from one point to another. We don't have like a fluid line. So let's just check. So when I look at this value right here, we're going to work with x equals 1, okay? And if I approach that from the left-hand side, alrighty, I can see that I'm at a value of 1. Okay, so I'm going to write that down. The limit as x approaches 1 from the left of my random function here is equal to 1. And then if I check my right-hand side, so the limit as x approaches 1 from the right of my random function here, when I come from the right, I can see that I'm approaching 2. Okay, so here the limit does not exist because 1 and 2 are not equal to each other. And so that's why this is defined as a jump discontinuity. Okay, and the third and final type is called infinite discontinuity. It's kind of in its name what type this is. And this is if one or both sides of the limit are equal to positive or negative infinity. So if you ever, even from the left or the right, you get positive or negative infinity, we call that an infinite discontinuity. So what I mean by that, right over here, okay, if I look at an x value of x equals 0, so that's the value I'm going to be approaching, x equals 0. When I approach it from the left, I'm approaching y equals infinity. And when I'm approaching from the right, I also get y equals infinity. So whenever you have infinity as an answer or negative infinity, it doesn't matter. If either side approaches infinity or negative infinity, that's an infinite discontinuity, okay? So let me write that down. The limit as x approaches 0 from the left of our random function here was equal to infinity. And also our limit from the right of that random function also equaled infinity. Okay, as soon as that happens, we have an infinite discontinuity. And these don't have to be equal. You could have one being a positive and one being a negative. These don't have to be equal to each other. Again, as long as you have one or both sides approaching infinity or negative infinity, you have an infinite discontinuity. Okay, so now that we have those down, we're going to go to our next page here. And these are those same graphs from Friday. And what we're going to do is we're going to look at each and every graph here. And determine if there exists a discontinuity, and if so, we're going to classify it as removable, jump, or infinite. And if it's one of these three, we have to justify. So we have to show what's happening in order for it to be that type. Okay. So remember, for a graph to be continuous, that means that the limit exists and it's equal to f of a. So when we did this graph on Friday, we were looking at x equals 0. Okay, so I am pulling that. If you want to, you can go back to your sheet and look at this graph from Friday, the first one, and you'll see that I was asking you to check the limit at x equals 0. So I'm going to use 0 again. Okay, when I approach from the left, I get -2. When I approach from the right, I get -2. So perfect. The limit exists at -2. And then when I check f of 0, I have a very solid defined point also at -2. So the limit exists at -2 and f of 0 is -2. So this is just continuous. We have no issue here. Okay, and if you want to add this to your notes, you can just write f of 0 equals -2. Okay, and -2 is also equal to the limit as x approaches 0 of this function. So that's kind of the notation. Okay, I have proven that this and this both equal -2. We are continuous. Okay, next one here. I see this, so I know I might have a problem here, okay? Typically, whenever you see a hole in the graph like that, everything else is nice and smooth, typically that's going to be removable, okay? But let's prove it. When I approach from the left of -1, this is the x value I'm looking at. When I approach from the left, I see that I have a limit existing at 1. And then when I approach from the right, I also have 1. So our limit exists at 1. That's good. But now, when I check f at -1, so I'm actually truly looking at the x value of -1, I see I have a hole in the graph. So it actually doesn't exist. So that's how we know we have a removable discontinuity. So I'll write down the notation here. I checked the limit, okay? So when I approached -1 from both the left and the right of this random function, it gave me an answer of 1. Okay, but that is not equal to f of -1 because we already proved f of -1 does not exist. So the limit does not equal the actual value at that point, and that's the definition for removable. Okay, on to the next. Okay, here we have a hole in the graph, but we also have this extra point. So what's going on here? Okie doke. So first, when I check the limit, which is typically how I always start, let's see if the limit exists. This was the x value that we were looking at on Friday. X is 0. Okay. When I approach x is 0 from the left, I get 2. Perfect. When I approach from the right, I also get 2. So the limit exists at 2. But now let's check, what does f of 0 equal? And you might be tempted to say at 0, it doesn't exist, but it does. Remember, we talked about that on Friday. We have that solid dot. So f of 0 does exist. We just have to look down and we see it existing at y equals 0. So here's the thing. The limit exists and this exists. They're just not equal to each other. Again, that is the definition of removable. Okay, so I'm going to write that down. I have the limit as x approaches 0 from both sides of this random function equaling 2. That was all good. But that is not the same answer I get when I check f of 0. Because again, I checked and f of 0 was 0. It wasn't 2. And that is the definition of removable, when those two are not equal to each other. Okay, next line, this guy here. All right, if I were in class, I would ask you, what do you think? This kind of looks the same as the question we just did. We have a nice fluid graph with a hole, but then we have another random dot. Let's also always check the limit. This was the value we were looking at, this graph, when we did it on Friday. When I approach from the left, I get a height of y equals 1. When I approach from the right, I also get y equals 1. The limit exists at 1, so that's good. But when I actually check f at 1, or sorry, -1, pardon me. When I check -1, this is my answer, not this. It doesn't exist there. So at f equals -1, or f of -1, it equals 0.5, and that is not the same answer I got for the limit. So again, we have a third in a row of removable. So here's your notation. When I checked the limit as x approaches -1 from both sides, it existed, and the answer was 1, but that is not equal to f at -1, because we discovered f at -1 equals 0.5. Okay, and you can even finish this off and say it equals 0.5, but what's important is you checked the limit and you checked -1, and they are not equal to each other, so removable. Okay, so I hope you're comfortable with removable, because now we're moving into jump. And like I said, you can kind of tell it's jump. We've got kind of two stretches of this graph, and we've got that gap, hey? So this was the value we were checking on this graph when we did it on Friday. X is 1. Okay, so let's check the limit. When I check the limit from the left side, I see that it's approaching -2. And when I check it from the right-hand side, I see it's approaching a y value of 0. So the left-hand side and the right-hand side limits are not equal to each other, and that's it. That's the definition. For jump discontinuity, we don't even have to check the whole f of one thing. It doesn't matter. As soon as we see the left-hand side not equaling the right-hand side of the limit, that is a jump. All right, and then I'll show you the justification you have to write. So we checked the left-hand side as we approached 1 from the left, of our function, of our random function, we got an answer of -2, and that is not equal to what we got when we checked the right-hand side of our function, which we got as 0. So our left-hand side does not equal our right-hand side, and that's the definition of jump. Okay, when you see this one, I hope you can tell right away that we're approaching infinity and negative infinity. So we're probably going to have an infinite discontinuity here, and I'll explain why. So if I check the limit from the left, and sorry, I'll just say this was the value we were checking. We were checking x at -1. When I approach positive 1. When I check positive 1 from the left, I'm going down to negative infinity, right? And when I go approach 1 from the right, I am getting infinity. And those don't have to be equal to each other, okay? The limit doesn't exist here because the left-hand side doesn't equal the right-hand side. So for sure, the limit doesn't exist. It is an infinite discontinuity, okay? So when I write my notation here, this is an infinite discontinuity because the limit as x approaches 1 from the left equals negative infinity. And that would be enough to call it infinite. But we also checked the limit from the right, and that equals positive infinity. Okay, again, these do not have to be equal to each other. That doesn't matter. Okay, so we have one side approaching negative, one side approaching positive infinity. That is an infinite discontinuity. Okay, so both of those occur. All righty, final row. Oh, sorry, final 2 rows. Okay, I hope you can see here it's probably going to be infinite again because we have both sides of the limit approaching infinity, and we were approaching x equals 0. So that is infinite because I have the limit as x approaches 0 from the left of our random function here equaling infinity, and it's the same on the other side that also approaches infinity. Okay, so this is an infinite discontinuity. Typically, when you see asymptotes, it's probably going to be infinite. Just kind of a rule of thumb. Okay. Ignore my doorbell. Okay, so my kids are going to come in, just ignore the noise. Okay, so now we have this going on. On Friday, this was the x value we were checking and approaching. Okay, x is 0. When I come from the left, I'm approaching y equals 2. But when I come from the right, I see that I am approaching a y value of 0. So let's write that down. My limit as x approaches 0 from the left of my random function is equal to 2. And that is not equal to my right-hand side limit as x approaches 0 from the right of my random function, because that one equals 0. So left-hand side doesn't equal right-hand side. That is the definition of a jump discontinuity. Okay, this one kind of looks the same. We've got that gap or that jump in the graph, right? So let's just confirm. When I approach that value of x equals 1 from the left, I am approaching a y value of 1, right? But then when I approach it from the right, I get a height of 2 instead. So again, my left-hand side doesn't equal my right-hand side. So if I write my justification, as I approach 1 from the left for my function, I get 1 as my answer. Okay, and sorry, I'm running out of room here, but that is not equal to the limit as I approach x from the right, because in this scenario, I get 2. So my left-hand limit does not equal my right-hand limit. That's how we prove we have a jump. Okay, I hope you're getting the hang of it. We have 3 more. All right. So let's check here. When I approach this value here, this was the value given on Friday, x equals 2. As I approach it from the left, I'm approaching a y value of 0. So my left-hand side is approaching 0. And then my right-hand side also approaches 0. So my limit on the left and my limit on the right are equal to each other. So when they are equal to each other, we then have to check, okay, what is the actual value of the function at that point? F of 2 right here, that gives me a y value of 0. So everything equals 0. The left hand equals 0, right hand equals 0, and this equals 0. When all 3 of those things happen, that means it's continuous. We don't have any issues here. Okay, and I'll just write the justification here. The limit as I approach 2, and I'm not going to put plus or minus because I checked the left and the right, same thing. So as I approach 2 from both directions of this random function, I get the answer of 0, and that is also equal to my function at 2. Both of them equal 0, so we're good, we're happy, it's continuous. All right, what do we have here? When we checked this one on Friday, we were looking at this value, so x is -1. All right, so when I come from the left and I approach x is -1 from the left, I have a height of 2. Okay, so my left-hand side equals 2. When I come at it from the right, I have a height of 1. So my left-hand side does not equal my right-hand side. You don't even have to check that. As soon as your left and your right do not equal to each other, that is a jump. All right, so here's the justification. Hi, sweetheart. X approaches -1 from the left is equal to 2, and that is not equal to the right-hand side limit as I approach -1 from the right, because that equaled 1. So my left-hand side does not equal. That's jump. Okay, last one. This one's unique because we can kind of see we don't have a left-hand side, right? So this is the value we were looking at on Friday. X is -1. We don't even have a left side. So all we do is we check the right side, okay? So as I approach from the right-hand side, I am approaching a y value of 0. So my limit equals 0 on the right, but I don't even have a left. So all I'm worried about is the right. So the limit equals 0. And then I check f at 1 also, and that also equals 0. So my limit equals my function value. So this is actually continuous, but I just want to show you one little extra thing here. I'm just going to show the justification. So the limit as x approaches 1, okay, of my random function equals 0, which is also equal to f of 1. Okay, so this is continuous, but because of this unique situation with no function on the left, what I want you to write is continuous, but then just add in from the right. That is just kind of us acknowledging that we see that the graph doesn't even exist on the left, and we've only really had to check the right. Okay, so you only have to do that if you just have a graph that's only on one side. Okay, but it is continuous, but just precisely from the right. Okay, so that's graph continuity and discontinuity. So the questions you're going to be working on are number 5, 6, 7, and 8. And for question 6, it actually asks you to use the graphs from Friday's questions. I believe it asks you to use the graphs of questions 1, 2, and 3. So that's what it means for number 6 when it says using exercises 1, 2, and 3, blah, 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 blah. It wants you to go back and look at those graphs. Okay? All right, that is it. I will see you tomorrow for your work period to work on these questions because there's quite a few of them. All right, have a good day.